to you how rich our universe is and what we can learn from it, not from just looking at the optical window, which gives a very narrow perspective, but across the electromagnetic spectrum from radio waves at a So I will focus because today is about an hour's lecture on just one of these windows, which is the radio wavelength that we'll talk about today. Let me start by showing you the very iconic picture of the black hole in M87, which was imaged just a couple of years ago at radio wavelength. This is at a wavelength of 1.3 millimeters. And what you can see at the bottom right is the shadow of a black hole, where light from the central region you do not see because that's where the black hole resides. And what you see around it is light which has been bent as per Einstein's theory of gravity to give you the kind of ring-like structure of material and light material around it. Now, this is essentially been done by connecting up radio telescopes, which are located at the South Pole to Hawaii, to Europe, to North America, and South America. So by joining telescopes together, one can get very high angular resolution, as I will just try to illustrate to you in a short while. So this image at the bottom right, which shows the black hole, is being imaged with a resolution of about 25 microarc second. Just to give you an idea of how small this is, that the resolution of the human eye is about an arc minute. Students of physics would know that it is proportional to the wavelength of the radiation that you receive and inversely proportional to the diameter of the antenna or the receiver or the telescope that you use. And the resolution which one is achieved to make this image right in the center of this galaxy called M87, which is in a nearby cluster of galaxies, has been 25 microarc second or so, which is equivalent to being able to observe an orange on the moon. So as small as that, if you put an orange in the moon and you can resolve it and see what the orange looks like, that is the kind of structures or resolutions that one has been able to achieve. To go back to a little bit of history, this particular black hole resides right at the center of this elliptical galaxy, a nearby galaxy whose jet-like structure or a linear feature was noticed as early as 1918 by Curtis, an astronomer of the time. But he didn't understand much about what was going on and just commented that it seems to be a linear feature in connecting to the nucleus of this galaxy, which looks elliptical in shape. Today we know that such sources launch jets of relativistic plasma, highly ionized plasma, which move out from the nucleus of galaxies at velocities close to that of light. This is what the blue light is, what you see is what this galaxy would look like at optical wavelengths. Suppose I were to image this at radio wavelengths, which has happened in the 70s and the 80s and the 90s, that this is what you see when you go to smaller and smaller scales. You see a nucleus right at the center. This you can see the scale of about 4,000 light years. You can zoom in onto this jet of plasma which is going on to understand a lot of the interesting plasma physics which is taking place in relativistic flows. As you get closer, you can see the jet on smaller scales, but you really needed the resolution of telescopes operating at very small wavelengths and with telescopes located across the world to try and look at right into the heart of the galaxy where the massive black hole resides. So this has been one of the most exciting findings in the last couple of years at the radio region of the electromagnetic spectrum. So this is just a blow-up of it to show that they have estimated the mass of the supermassive black hole. I missed out a number over here. It's about 6.5 into 10 to the power of 9 solar masses. So it's several times a billion solar masses. And we talked about 4,000 and 2,000 light years. The diameter of this ring is about 1/100 of a light year. So you can see a billion times the mass of our sun squeezed into a tiny, tiny fraction of length. So this is what are the kind of physics that we want to try and probe and understand as to how these black holes formed and grow, how do they actually squirt out relativistic plasma at speeds which are close to that of light. You know that light is the maximum velocity that one can achieve, and light from the sun takes about 8 minutes to reach us, and about 1.3 seconds from the moon. And, and this is plasma which is squirting out from the nucleus of an active galaxy at velocities which are close to that of light, not that of quite that of light, but a fair fraction of the velocity of light. So this is a long story, and today I will tell you a little bit of that story of how it began and some of the exciting results and some views into the future about what the next generation is going to look at. But before that, I thought I would just tell you a little bit about galaxies, which are the basic building blocks of the universe. And as you all know, galaxies are aggregates of billions of stars. Some are large, some are small. And the bulk of them in the nearby universe can be classified into those which are either spiral-like in shape or elliptical-like in shape when seen on the sky. Some are irregular, including the nearby galaxies, the Large Magellanic Cloud and the Small Magellanic Cloud, which were catalogued by the historian Pigafetta that Magellan carried along with him in his voyage around the world. And so these two galaxies are named after Magellan and his voyage. But galaxies don't occur in isolation. They occur in groups and clusters. They're part of a much larger cosmic web, of which we are a very small, tiny fraction living in a nondescript part of the universe. The left montage shows you pictures of galaxies actually colliding, which are in groups. Due to the gravitational attraction of one upon the other, they can tear each other apart. Smaller galaxies can be swallowed up by bigger ones. You can sometimes surprise a galaxy at its dinner. And this is the way they have evolved over cosmic time. And what we see today is a result of their evolution since the universe first started off. On the right, what I've shown you is a deep image taken by Hubble Space Telescope of a region of the sky where there are not many stars, no bright stars. And every dot that you see over there is a galaxy, some relatively nearer and some at the distant edges of the universe when galaxies first formed. Every dot over there is a galaxy. There are about 10,000 galaxies over there. So galaxies, although the universe on large scales is homogeneous and isotropic, but on small scales they form all kinds of structures. Because we are inside our own galaxy, the Milky Way, we cannot actually take a picture from outside like the external galaxies. We can't move out of our galaxy and take a picture. But this is what it looks like to us when we see from the Earth. I remember as a child in Shillong, we could make out the Milky Way. Today in cities, it would be difficult, but if you go to rural Assam, you would still be probably able to make out a faint, fuzzy, sort of elongated structure, the Milky Way in our galaxy. The arrow over here points to the center of the galaxy, which we will meet later again in today's lecture. These are city lights over here, don't worry. This is taken from an observatory in Chile. Now, this is an optical view of our galaxy, which I showed you, if you were to reconstruct it. And you can see that there are dark patches as well, in addition to the light which you see is from the stars. The dark patches are because of dust and gas, which obstructs the starlight from behind it. The stars contribute most of the mass of the galaxy, just like our galaxy of the visible matter, but the volume is filled up with material between the stars, which is called the interstellar medium, consisting of gas and dust, from which the next generation of stars form. So our galaxy, like all other galaxies, are not passive structures, but they're all evolving passively. New stars are being born and old stars die. And how they die depends upon how massive they are. And as I said, galaxies are not isolated, they are in groups. We are also a member of a small group of galaxies called a local group, which consists of about 50 members. Most of them are very small galaxies called dwarf galaxies. The nearest galaxy is the Andromeda, big galaxy is the Andromeda Nebula, which actually, due to the gravitational attraction of one another, is coming towards us and should collide with our galaxy in several billion years as well. But when you plot a distribution of galaxies, you see what is called the cosmic web. They all are form filamentary structures, and these are related to the way galaxies formed from the initial perturbations that led to the formation of structures in our universe. So this is a wonderful world, a beautiful world of galaxies. Inside the galaxies, we have, as I said, have stars, billions of stars to millions of stars, depending upon how massive the galaxy is. And there are lots of tales and myths woven around them. And the stars, as you know, are powered by nuclear reactions which take place in the center, but they may have different colors depending upon what the temperature of the star is. And that depends upon its evolutionary stage and the mass of the star. I'll not digress into telling you about stellar evolution today, because today's story is about learning a little bit more about the radio window and what it has revealed towards us. As I just said, that astronomical observations till the 1930s were confined largely to the optical region. Fantastic discoveries were made by the ancient Greeks, Hipparchus, Indian astronomers like Aryabhatta, and countless others. The Islamic science which flourished, and you can find it in names of stars, whether it be Algol or algorithms, mathematics, etc. But it was Herschel who discovered that there is radiation outside the optical window. What he did was a very simple experiment. With a prism, he broke up the sunlight into its colors and just put a thermometer beyond the red end, and he found that the temperature rose. So there was radiation beyond the red end of the spectrum. But strangely enough, he didn't put a thermometer at the other end. It was left to Johann Wilhelm Ritter, who found emission at the ultraviolet wavelengths a year later. So today, except for these little forays outside the optical window, we did not know much about the universe, and we did not expect very much either. And it is interesting to note that the radiation from the sun peaks at a wavelength through which the radiation comes through to reach us. And I'll mention a little bit more about that in a little while. Today, to study the universe, we look at the entire range of the electromagnetic spectrum from gamma rays to radio waves. Not only that, we study cosmic ray particles, which are high-energy particles, electrons, protons, and heavier nuclei, which are generated in very energetic events in the universe. We study neutrinos, antineutrinos, neutrinos, which are generated in the interiors of stars when nuclear reactions generate power. And it is a detection not only of the neutrinos, but of the right number as predicted by theory, led us to believe or put our solar models or the stellar models on a firm basis. Then we also study solid constituents, interstellar dust grains, which spacecrafts might pick up, meteorites, lunar samples. We have had a spacecraft land on an asteroid, which is going to bring samples back to us as well. And of course, the new window of gravitational waves, which is predicted by Einstein. So today we'll focus on a very narrow part of the wide range of messengers of information, or multi-messenger information, to study our universe. As I said a little while earlier, that today, if you look at the universe, it's the optical region of the electromagnetic spectrum that is visible to us, and also a range in the radio region of the spectrum. Almost all the other radiation is blocked by the atmosphere. At long radio waves, it is blocked by the ionosphere, as the long wavelength waves cannot penetrate the ionosphere. But in this radio region of meters to millimeters or centimeters, it passes through unhindered, and the optical region, it comes through. If you think for a moment, we are extremely fortuitous that the sun's peak, the sun is at a temperature where the peak in the spectrum lies in the optical region of the spectrum. And the fact that our eyes are also sensitive to this region must be due to the biological evolution of the human eye. And this is just another sort of illustration of it, that if you want to go above the ionosphere, we need satellites, rockets, balloons, aircrafts, depending upon the experiment that you do. Today it is almost entirely by satellites, but in the early days, rockets, balloons, and aircrafts were also quite commonly used. And water vapor and carbon dioxide are the two of the principal culprits which block the radiation from coming to us. What about the radio window? The radio window is indeed very large. It goes from about 1 millimeter, I said, to about 30 meters or so. So it's a ratio of 30,000 to 1. Compared to the visible range, which is about 400 to 800 nanometers, just a factor of 2. A radio wavelength, as you can see, is basically anything that you can measure with a ruler. For 30 meters, you'll have to take the ruler many times, but it is something you can measure with a ruler. But all is not well with communication, the mobile phones that we're using, TV entertainment that we see, civil aviation, you name it. Each part, each window, each band part of the window is highly contested, and there are huge commercial interests in it. So radio astronomy, there's certain very important bands which are protected, and radio astronomers will try to go to regions where there is very little of radio interference to try and set up radio telescopes so that you can try and make these very sensitive observations. Today, even in the early days of radio astronomy, the unit which was used, called the Jansky, is about 10 to the power of minus 26 watts per hertz per meter squared. And today we are operating at micro Jansky levels. So you can see the very little power which we get can be easily swamped by man-made sort of sources of radio noise. Let me go briefly into a little bit of history and tell you about how it all started off. This was due to a person called Karl Jansky, who was an engineer at Bell Laboratories, and he was given the task of finding out sources of man-made interference or interference generally to that might hamper communication across the Atlantic. So he built an antenna which you can see over here, operating at 20.5 megahertz, and what he detected were sources of electrical disturbances, that is man-made sort of thunderstorms, distant thunderstorms, nearby thunderstorms. But he noticed a very small hiss, which was of no use for communication. So Bell Labs was not particularly interested in that. But Karl Jansky pursued it. He pursued it and made lots of observations to find out where the noise came from. And he found that it came a little bit earlier every day. And that would happen if it came from a celestial source rather than a terrestrial source. And he ultimately pinned it down to radio emission from the center of our galaxy. This was not predicted by theory. This was not expected. This was just an observer doing an experiment who wanted to get to the root of everything that he saw. And that is an important lesson for young persons doing research. A lot of discoveries are not because they're predicted by theory or people thought about it, but nature is rich and beautiful, and a lot of the discoveries are serendipitous, which has made monumental changes in the development of science and the history of science, which actually most of the philosophers of science don't take account of while tracing the history and the development of science. Karl Jansky, after he discovered that, went back to work at Bell Labs and didn't pursue it further. And it was left to another radio astronomer called Grote Reber, who was not employed at that time. And he built an antenna in his backyard, literally in his backyard. And apparently, there were observations available on Mondays because his mother used to use a line over there to hang up her washing. So it was literally in the backyard. And he tried to detect the radio waves which Karl Jansky had detected. And he initially did his observations at high frequencies, 3300 megahertz, then at 900 megahertz, and he didn't succeed. He moved lower in frequency and detected the emission at 160 megahertz. This was very important because it showed that the emission is more prominent at low frequencies than at high frequencies. And this was quite unlike the kind of radiation that physicists were used to at that time, which was you heat a body, it radiates like a black body, or you heat a gas and there is thermal emission, free Brand-Strahlung emission. But it was a completely unknown kind of emission over there, found serendipitously again. And it was left to a number of astrophysicists, notable contributions from the Russians, Ginsburg, Syrovetsky, Shklovsky, and others, to realize that this was due to ultra-relativistic particles which are moving around in the weak magnetic field of our galaxy. This is true not only of our galaxy, but of other galaxies as well. So this heralded the beginning of radio astronomy globally. In India, it was left to this person, Professor Govind Sarup, who was my guide, to lay the foundations of radio astronomy in the country with some state-of-the-art instruments which he built. So this is the group I worked with for a long time. On the top picture, you see a picture of the UTI radio telescope, which operates at a frequency of 325 megahertz. And at the bottom, you see the giant meter wave radio telescope, which is located on the outskirts of Pune, about 80 kilometers north from it. So this is about half a kilometer long and 30 meters wide. And you don't clearly see the reflecting surface. You can see sunlight reflected over here. Because the wavelength is long, that even thin stainless steel wires separated by about 1/20th or so of the wavelength of light acts as a perfect reflector for these long wavelength radio waves. If you had short wavelength radio waves, then you would have filled apertures, but otherwise these act as very good reflectors. These are 30 antennas spread over 25 kilometers, and all the signals are combined as though they're from a single antenna. So it's like the city of Guwahati entirely being a single antenna, by placing antennas in different locations and trying to combine the signals in your computers and getting the kind of resolutions which you would get from an antenna of that dimensions. Now let's look at the radio sky. The radio image of the sky, this was a map which was made by Glenn Haslam, a friend, along with his collaborators in 1982, combining data from telescopes in the northern and southern sky. And if you recollect the optical image which I showed you dark patches over here. There are no dark patches at all. This is largely synchrotron emission combined with free emission, which is from hot gas, which is heated up by the stars. And this is what our galaxy would look like when looked at, when seen at radio wavelengths. If I zoom in a little bit, let me just introduce two concepts over here, just for students of physics. I will not take too long over here. That the resolution is given by 1.2 lambda by d. Lambda is the wavelength of observation, and d is the diameter. And as I mentioned, that for the human eye, it's about an arc minute or so. Because your pupil changes size, it will also depend on whether it's daytime or nighttime, and the sensitivity of a telescope depends upon how big your collecting area is, and also a very low noise receiver system, so that your receivers and electronics also don't contribute to the noise. This operates at high frequencies, so unlike in the GMRT, you can see that this has to be a filled, not only a filled, a very accurate paraboloid, so that the wavelengths, so that all the lights are reflected properly into the focal point over there. This is another telescope which I used extensively for my PhD, located in the plains of New Mexico. This is called the Very Large Array, and these are 27 antennas. But what they do is they have railway tracks over here, and they can move them along the railway track, so that when they're much further away, you can observe sources with much higher resolution than when they're closer away. So small separation means coarse resolution, because D is small, whereas when D is large, you can find higher resolution. Just keep that in mind when we keep talking about resolutions. Just to give you an idea of what the kind of resolutions that we get, I told you about micro arc seconds. That is even much better than that. But if I took a 5 rupee coin and put it at a distance of 1,000 kilometers, it would subtend an angle of about 4.7 milliarc seconds. And 1,000 kilometers is roughly the distance between Lucknow to Guwahati. So you'll be able to say the structure of a 5 rupees coin if somebody holds it up in Lucknow for you from Guwahati. And in fact, with the Event Horizon Telescope, which has mapped a black hole, it has gone into about 25 micro arc second level, much better than that. So you can see the kind of angular resolutions, the kind of detail one has been able to see by the techniques which radio astronomers have developed, and which have had wide other applications as well. With low resolutions, this is what an image in the sky might look like. This was a long time ago, 12 arc minutes, but I've already shown you images of the kind of detail which one sees when observes on objects with higher angular resolution. So let me try and tell you a little bit. This will be a biased selection of objects that I will try to highlight. I'll finish before 4 o'clock so that there is time for questions and interactions. Now, what I want to do is, suppose I had a radio image of the sky. I can't do very much with it except to say that there is image continuum radio emission from that region of the sky. So to try and find out what these objects might be, one of the natural things to do is to try and correlate with the optical images of the sky and see what they are associated with. Do they lie bang on optical galaxies? Or do they lie in some stars? Or do they lie in a class of exotic objects we have not yet seen? Now, through that process, they found that some of these very strong radio sources, I will not get into too much of detail, but just give you a glimpse of it, were associated with galaxies. nearby galaxies by and large at that point of time, because if they're very distant, the angular size would be small, there would be too many optical objects associated with it, identification would have been ambiguous. And when you try to map these objects with high angular resolution, then you found that they were not like the optical galaxies at all. The optical galaxies, right, sitting in this little box over here, which is blown up in the picture shown below. But what you find is objects where plasma is squirting out to form huge lobes of relativistic plasma, giving rise to emission, which is due to these relativistic particles gyrating in magnetic field, called synchrotron emission for those who are students of physics. And these sources can extend up to millions of light years. 1 parsec is 3.26 light years. That is the distance light travels in a year. But there are sources which are many megaparsecs in size, as I will just show you in a very short while. And this is another example of a radio galaxy. This is superposed on the optical picture. You can see the optical image over here, and you can see this jets of plasma coming out periodically, blowing plumes of plasma. And the whole energy content in these lobes is about 10 to the power of 60 ergs or so. So there are a lot of challenging astrophysical questions related to the generation of these huge amounts of energy, the collimation of flow over distances of billions of light years, and the huge energy output over the time scales that we see that these lobes of emission exist. By the same process of identification, one found new and exotic classes of objects. I will just highlight one of them, and that is these are objects which are called quasars. Quasars are distant objects, and they appear star-like in optical images. Today we know that they are very powerful luminous nuclei sitting in powerful objects, powerful nuclei in galaxies, but in the good old days they just looked like stars. So when a radio source was found associated with it, there's an interesting story as to how that was done, but it will take up too much time, that it was indeed quite a surprise. Because stars generally are very weak emitters, and it was by measuring the distance, which is due to the redshift, which is due to the cosmological expansion of the universe, one realized that these are objects which are very far away. 760 million parsecs. 1 parsec is about 3 light years, so you can see it's more than 2,000 million light years away. So these are the kinds of distances, and these are relatively nearby objects by today's standards. Today we have literally gone almost to the era when galaxies first formed. But again, the quantity, the energy which it generates, not merely in the radio, but right across the electromagnetic spectrum from X-rays to gamma rays, is million times larger than that of our sun. Okay, 10 to the power of 47 ergs per second, whereas our sun is about a few times 10 to the power of 33 ergs per second or so. So you have huge amounts of energy generated from objects which look star-like in our plates. So these are the challenges which astrophysicists have had to deal with in terms of understanding the physics of these objects. Okay. So the physical process, as I just mentioned earlier, is largely due to synchrotron emission. There are other exotic processes going on in the central regions, but I will leave that alone for today. While on this theme, I thought I would at least share just a handful, just sort of a sample of some of the interesting results which I and my collaborators have found from the Giant Meter Wave Radio Telescope. This is actually the largest giant radio galaxy. It is the largest single structure that is known in the universe. It is still, when we did it about 12 years ago or so, when we reported this object first, I mean, the number of sources which are large have increased manifold. The number of sources which have also observed manifold. You know, there are millions of sources which have been sort of cataloged now, but this still continues to be the largest giant radio source galaxy, a single object, with a distance of 4.7 megaparsec. As I said, 1 parsec is 3.26 light years, so it's about 20 to 23 or more than that million light years across. So again, we tried to model this source in terms of both the jet power from it as well as the environment to which it is going out. Here you can see an image of where the black hole jet may be processing, and you can see this beautiful structure spread over 1.9 million parsecs. 1 parsec, as I said, is 3.26 light years, being imaged by a student I'm working with who will defend his thesis from Leiden University in a few days, Pratik Davade. And this is a beautiful object which we again found a new where the emission down again to give you a new. So these are aspects as to why galaxies switch on and off are interesting questions which we try to understand applying basic physics. In addition to the kind of galaxies which I showed you right now, there are also galaxies which exhibit intense bursts of star formation. If I look at the star formation rate in our own galaxy, by various means, I can estimate it to be about, few solar masses per year. Those are the estimates, a couple of solar masses per year. That would be the kind of star formation rate in our galaxy. Because the massive stars, they die in massive explosions called supernovae, which can outshine a galaxy sometimes. And some supernovae have also been recorded historically by the Chinese, the Americans. There have also been, in the Middle East, there have been reported records of it. Unfortunately, there have not been any sort of good Indian records of it so far. But in these starburst galaxies, it's like Diwali crackers going on. That there's an intense burst of star formation, about 100 to 1,000 stars, solar masses per year, new stars form, they die, and you can probe right into the nucleus and understand star formation processes while probing the central regions of these galaxies via radio windows. So as I said, I was going to give you just a sample of results and not be exhaustive. This is an image of the sky, of the whole sky, after subtracting out the emission from our galaxy, which we saw earlier, and also emission from sort of sources, known sources in the sky. This is an image of what is called a microwave background radiation. When the universe evolved from a hot Big Bang, which seems to be the overwhelming sort of the consensus of opinion now, it went through a phase of a very hot fiery past, and about 380,000 years or later since its birth, today we know the universe is 13.7 billion years or so, that the radiation decoupled from the matter and the radiation has cooled. This was predicted by George Gamow, who worried about it. Arno Penzias, Robert Wilson were the ones who detected this radiation, which as the universe expanded would have cooled. And Penzias and Wilson actually got a Nobel Prize in physics for discovering this. They were working at Bell Labs with a Horn antenna. And again, there was residual radiation, which they had to sort out and found it to be the cosmic microwave background radiation. The interesting historical asides about how these radiation were discovered, but someday maybe I'll talk to you about the history of and philosophy of science and tell you some of these stories. But this is the most perfect blackbody radiation that we know of. The whole universe is radiating, and this is at a wavelength corresponding to a temperature of about 3.7 degrees Kelvin. This is the lowest temperature that we have, just a mere 3.7 degrees Kelvin. 0 degrees Kelvin being the absolute zero of temperature. From the large scale of galaxies and the universe, let me tell you a little bit about small scales. Okay, small scales. This is a picture of what is called a supernova remnant. This is when a massive star explodes at the end stages of their evolution. This doesn't happen to a low mass star like our sun. Low mass stars die more quietly, like a poor old man, whereas these rich or more massive stars end their lives in these catastrophic explosions, which gives rise to a huge amount of flux at all kinds of energies, high energies inclusive. They also release neutrinos, which are detected from the supernovae, which went 1987A, which went off in the Large Magellanic Cloud, and were detected independently, again confirming our theories and our understanding of the evolution of massive stars. Here, red is the radio, optical is the green, rays are blue. And there is highly ionized gas as well, which gives rise to emission lines as well when the atoms recombine. Okay, so this is the kind of structures which you see of supernova remnants after they've exploded and they have evolved. And they keep expanding with velocities of thousands of kilometers per second and ultimately disperse into the interstellar medium of the galaxy. Now, when these massive stars evolve, they leave behind a remnant so dense that about the mass, that the entire mass of the sun would be contained in a star which is only about 10 kilometers in size, much smaller than the city of Guwahati, and the entire mass of the sun compressed into it. So material over here exists not as matter as we know it. I mean, it's largely made up of neutrons and is referred to as neutron star. And because of the momentum which is imparted to it, these remnants rotate very rapidly, and the magnetic fields with which the star was associated with it, they get compressed into the small structure, and you have magnetic fields which are of the order of 10 to the power of 12 Gauss or so. Very strong magnetic fields, and these strong magnetic fields accelerate particles along these magnetic field lines, and they're spinning around, and in the spin axis is different from the magnetic. Come to your line of sight when it is come to your line of sight periodically as it is rotating. So what you will see are pulses of emission, as is shown in the GIF file on the right. The other background objects are steady, but the pulsar keeps rotating. And pulsars can rotate very fast. This pulsar was discovered by Jocelyn Bell Burnell at Cambridge while she was looking for scintillations of radio sources. Just like the stars scintillate due to irregularities in the atmosphere, compact radio sources scintillate due to irregularities in the ionosphere, in the interplanetary plasma, the plasma that pervades the medium between the sun and the earth. And while she was doing that, she noticed the periodicity which could not be due to the interplanetary plasma. Initially, they thought it was some alien civilization and they called it the little green men, but they soon realized that it was actually just basic physics of neutron stars, which were worked out earlier, which they could apply and understand the end phases of stars. Today, there are a lot of these pulsars which have been cataloged, thousands of them actually, and they have become very important sources of study, as I will mention a little while earlier as well, not only in terms of studying stellar evolution, but also these pulses are very accurate. Sometimes there can be glitches, just like earthquakes, there will be star quakes or pulsar quakes, there will be glitches in the period, but otherwise the periods are so steady that a group of them preserves time more accurately than that of an atomic clock. And the fastest star that we have, or pulsar that we have, as we call them, is 1.3 milliseconds or so. So every 1.3 millisecond, the star is rotating. So you can imagine how rich the universe is, which has been opened up by looking at the radio window. So these were the pulsars were discovered at the radio window, but now we know we also detected a smaller number though of pulsars. So far, let me keep an eye on the time. Okay, I have about 10 or 15 minutes more. So far, I've talked about emission over a large frequency range. Okay, for example, if you heat a block of iron, radiation is emitted over a large wavelength range. The star emits over a large wavelength range. But if you look at spectral lines, for example, when you look at a transition of an atom from one level to the other, those would be very narrow emission. They would be restricted to the transition in energy from one level to another. As students of physics will tell you, the energy levels are quantized, and you have very narrow emission or absorption lines, depending upon whether it is emitted or absorbed. In the early 40s, we knew that hydrogen was the most abundant element in the universe. And a lot of the universe, a lot of this hydrogen could be very cold. And it was Jan Oort, a very legendary Dutch astronomer, who asked one of his students, Van der Hulst, to try and see if there was a line from hydrogen which could be observed at, or line which could be observed at radio wavelengths. And he predicted that there would be a line at a wavelength of 1420.405752 megahertz, which is a wavelength about 21 centimeters, slightly so shorter than your 1-foot ruler. And this is because of the spin of the electron and proton being aligned to the spin and proton being parallel and antiparallel. This is known as a hyperfine splitting for those who are familiar with the term, but otherwise don't worry. But remember that it is a very low frequency. transition, and this is hydrogen which is very cold, because if it is hydrogen which is very hot, then it would be at a higher level, or it would be completely ionized and recombined, and you would see lines in the optical or ultraviolet, etc. But when hydrogen is in the ground state, it's cold, it's about only 100 degrees Kelvin, even lesser probably. How do you see this line? Then atoms, the electrons are all in the ground state. This is the only way you can detect it. And this is proved phenomenal in trying to understand galaxies and the universe. Formation of galaxies. How does the gas content change at cosmic epoch from the time the universe formed? How did galaxies form? How did star formation change? Because ultimately star formation is related to the gas content. And this has been one of the invaluable tools. Atomic hydrogen radiating at 20 centimeters. This is just another illustration to show you the same effect effectively without getting into too much of technical detail. And this is Fanny Hurst in 44, predict hydrogen emission at 21 centimeters. And this was the early Westerbork telescopes, which was one of the telescopes which was predicted, which was used to detect a line, first reported detection of the line. In addition to that, a universe, we are aware of complex molecules. We are aware of the molecules that go into forming life, the DNA, RNA chains, proteins, etc. And the whole field of astrobiology, astrochemistry has actually really developed over the last several decades. We can detect what are called recombination lines from very high quantized levels of hydrogen atom or other atoms, which occur at low frequencies because the energy levels at those high quantum numbers are small. And you can detect complex molecules from quantized, rotational, vibrational transition levels of all kinds of different molecules, from alcohol and water vapor to cyanodecapentine, methane, you name it. Okay, so this astrochemistry is important in terms of understanding the formation of molecules. And these molecules sometimes, and not only those transitions, but sometimes just like lasers, you have emission, amplified emission at microwave wavelength called lasers, where there is an inversion of population, and there's been maser emission, which has been detected from water vapor and other maser emissions as well. And I just want to illustrate to you one very cute example of what radio frequencies can do in trying to probe the nuclear regions of active galaxies. This is water vapor maser emission spread over, this is around 22 gigahertz or so. And what they have done using very high resolution, using antennas spaced very far apart, they've tried to find out not only where a maser is coming from, but with what velocity is this moving out. Then you find that one side it is coming towards you, and the other side it's going away from you. So one side is red shifted to longer wavelengths, the other is blue shifted to shorter wavelengths, and then it's like a rotating disk over here around the nucleus of this galaxy. And just as the planets rotate around the sun, you can go and apply Kepler's laws and see what the central mass should be. You know the distance to the object, so you know the scales that you're looking at it, you know the velocities, and you can estimate what is the mass of the central black hole or the central object. So this is about 40 million solar masses or so. The black hole at the center of our own galaxy is about 10 times smaller. Now, neutral atomic hydrogen can be used to, as I said, I'll just give you one example of it, it's because of shortage of time, to study galaxies. And let's see what wonders it has revealed to us. Let's take an H1 cloud over here, just a cloud of neutral atomic hydrogen associated with a galaxy. And as I said, that one side would be blue shifted, the other side would be red shifted. So this is given in velocities. So one going away from you is a higher velocity one coming towards you is a smaller velocity one. And in the central region of the galaxy, usually there is less hydrogen. So you get a dip in the center, but the extreme values will tell you how fast it is rotating, how fast the whole galaxy cloud is rotating. Our galaxy is also rotating. I mean, we think of only the motion, normally think of the motion of the Earth around the sun, but our sun itself is going around the center of our galaxy at about 220 kilometers per second. Just imagine the kind of speeds at which you're moving around, but we're completely oblivious of it. We have got so tuned to non-accelerated motions over here. So let me just tell you a little bit about hydrogen in galaxies. So we can study the dynamics of galaxies using the atomic hydrogen, as I said, because hydrogen is a line which emits at a specific frequency, so it can be shifted to higher or lower frequency depending upon its movement, just as the frequency of a train whistle changes when it is coming towards you or away from you. But those are longitudinal sound waves. These are transverse electromagnetic waves. So one shouldn't stretch the analogy too much. Here is a galaxy, and the white part which you see is the optical galaxy. All these white dots are background objects, stars, more distant galaxies, etc. But the blue is atomic hydrogen. So you can see that atomic hydrogen can sometimes extend well beyond what your eye or what your optical wavelength shows us. So the universe is rich and manifests itself in diverse forms, as I said. But let me try and illustrate to you a little bit of what this kind of study has revealed. Here are just H1 or neutral atomic hydrogen maps of galaxies. Red is just red shifted, blue is blue shifted. You can see the rotations of these galaxies, but there are also non-circular or chaotic motions sometimes, which tells us what is going on inside the galaxy. But let me try and illustrate, spend a minute on this, because this is something which is extremely interesting and relevant. I can go and measure the velocity of outer planets over here, all right? Of the planets as I go away from the sun, all right? Now, as you know, the orbital speed will decrease as you go further and further away, and this is nothing but the application of Kepler's laws of planetary motion. If you balance the centrifugal force with the gravitational force, you'll get 1 upon root of r dependence, and this is what you expect, all right? And this is what you'd expect. Now, if a galaxy has most of its mass concentrated in the center, okay, initially if the mass builds up very much, you might actually see a rising kind of curve. But once most of the mass is taken over, you should see a velocity which keeps dropping as you go further and further away. But lo and behold, that is not what you see. What you see is that the velocity doesn't fall down. You find that the velocity just remains a constant. If the velocity remains a constant, then there has to be material outside it, beyond what we can see, beyond what we can see in all regions of the electromagnetic spectrum. Not just atomic hydrogen, but all the gas and stars that exist over there, molecular gas, whatever it may be. You can account for all that, and you still find that you cannot explain this. If you account for all the material in the disk, this is the way it should come back. So this leads to the suggestion that there is matter which you cannot see, but whose manifests itself through its gravitational influence from the dynamics of galaxies. There are other arguments as well. And this is what we call dark matter. We don't know what it consists of. It is still one of the very active areas of research. There's some clues, but we don't really know what it is. But we know this matter exists, and we know that it makes up about 23% of the universe, of the present universe. All the galaxies that I showed you and I, and all the buildings, and all the cities, the planets, and the Earth, they just make up 4% of the constituents of the universe. 23% is dark matter, which I've shown you from observations of neutral atomic hydrogen. So I've just tried to select a bunch of results with my own biases. Some would say that you have not spoken about the sun. Some would say that I've not spoken about the epoch of reionization. So there are a lot of interesting objects, or objects in the universe at radio wavelengths which I have not touched upon, planets, etc. I've just given you a glimpse of what we can study. There is much more. Now, what is the next step? What does the future tell us? So I'll spend a few minutes on that, and then we will close and take a few questions. So the next major development in radio astronomy has been to build a large telescope. Okay, large telescope which is far more sensitive than what it is today, and this requires the collaboration of not just one country but dozens of countries, and this is over a dozen countries which have collaborated to collect this huge collecting area called a square kilometer array. Okay, and India is also a part of this collaboration, and this is because of various restrictions. It has now been restricted to what they call SCAR-1 in 2 frequency ranges, mid-frequency range from 350 megahertz to 15.3 gigahertz, and at the low frequency range, which is from 50 to 350 megahertz. This is being built in South Africa, okay, in completely desert-like area. You can see over here that there is no sign of human habitation. So satellites will still screw up things, but at least human man-made sources of interference, industries, cell phones, etc., all that is minimized. At its present SCAR Mid-1 stage, it will consist of 197 dishes with a maximum baseline of 150 kilometers, and resolutions will range from about zero point 0.7 to about 40 milliarc seconds or so. I talked about millijanskis and millijanskis. These will actually go to sensitivities of about a microjansky or so. So it'll be far more sensitive. And the plan is that when the full SCAR comes on, there'll be many more antennas spread across a certain part of the African continent. And the SCAR low frequency one, these are antennas which are tree-like, located in Western Australia. And Western Australia, for those of you who may have gone there, is absolutely desert-like. Here again, there is no human habitation. So man-made interference is very, very low or non-existent almost. And there would be 13,100 antennas in 512 stations. Okay, I think this is spread over about 65 kilometers right now, but it will expand later. And resolutions, because the frequencies are lower, it goes to about 11 to 4 arc seconds now, and sensitivity is about 14 to 26 microjanskis or so. So these results have started coming out from an early version of this. There was a telescope called Meerkat, which the South Africans had built, and which had given stunning results till now, and that is going to is being integrated with the square kilometer array being built at South Africa. These are just some of the stunning images which has been made by the Meerkat telescope. This is the center of our galaxy. Some of it we knew, but there are all kinds of interesting, probably magnetized filaments. The center of the black hole, the center of the galaxy is over here. The supernova remnants, regions of ionized hydrogen, and this image has been made with a Meerkat. I just showed one image of our galaxy, one outside our galaxies, similar to the galaxies which I showed, but you can see a nice X-shaped structure illustrating the flow of the plasma in multiple directions, possibly guided by density gradients and also precession of a central engine. So these are some of the very early results to come out from Meerkat, but once this whole array is complete, it will be one of the major developments in radio astronomy. And there are a whole variety of questions which one hopes to address, right from galaxy evolution, as I said, detecting hydrogen from very early epochs, understanding how star formation has evolved, strong field, that means in a field of strong gravity, using pulsars and black holes, timing of pulsars to test Einstein's theory of gravity. I mentioned about magnetic field, trying to understand how these large-scale magnetic fields have formed. How did the first stars form? How did black holes form and evolve? Are we alone in the universe? Can we detect signs from intelligent life elsewhere if we have much increased sensitivity? Or are we going to detect molecules which may be signatures of life? There were claims of detecting phosphine from Venus, but that claim has since been withdrawn. But are we going to find signatures in molecules? Today there are many thousands of, over 4,000, if I remember correctly, extrasolar planets, and many of them, a significant fraction of them, is what is known as a Cinderella zone or the habitable zone, where temperatures and availability of water are likely to be there from the definition of life as we know it. Okay, so cradle of life, understanding how life originated, is something which is very fundamental to us. And gravitational waves, what LIGO, what black hole reports they have come so far, have detected black holes in high frequency ranges, but with accurate timing of the pulsars that I talked about, which are like atomic clocks, that if there are gravitational waves traversing through space, that they would introduce changes in the pulse of the pulse arrival times or the pulse periods. And by detection of those changes, you'll be able to infer gravitational waves in a nanohertz frequency range. In fact, several friends of mine and colleagues are involved in timing pulsars accurately. There is not only an international planetary timing array There is one at Parkes called a pulsar timing array. There is also an Indian pulsar timing array using both the GMRT and the UT radio telescope, which several of my friends are involved in, which are tying up with the global community. Science is global. We cannot pretend otherwise. And that is the way that science develops, by sharing, whether it be genome structures of the coronavirus, or whether it be data from gravitational waves. Science progresses by collaborating, sharing, and that is very fundamental. And I hope governments understand that in depth. But I'll close by just one last comment, that with the story of the development of radio astronomy and some of the discoveries which I mentioned to you were entirely serendipitous. They were discovered accidentally. That is true of the history of science in many other instances, but particularly in astronomy, because the universe is so rich and we don't know what to expect. New objects are being detected, or new kinds of objects are being detected every time. Today, I mean, it's only recently that there were very fast radio bursts which are detected, which you didn't know anything about earlier, and which are not predicted by any theory either. And so as young students, when you go forward in research, it is actually delving into the unknown. Pay attention to things which you don't understand, even if the effect is small, because these are the harbingers of something which may be very profound. And not all things that you pursue will work out. Maybe just 10%, maybe just a few percent. But just as a footballer plays with all his energy to score a single goal, you have to pursue research with all your energy to hopefully make one small dent, one small discovery. So I will close at that and perhaps take a few questions. Thank you very much.
Thank you, sir. Thank you, sir, for your beautiful presentation and your suggestion and comments. So I request, if anyone is having any questions, so you may unmute yourself and we may go for the discussions. So anyone having any? Yes. Sir. Sir,
I think Chancellor sir is speaking, but
I think you have to unmute yourself. I think you'll have to unmute yourself. Narendra, unmute kori laba lagibo. It's unmuted now.
Okay, actually, it's very fascinating and very interesting. We know Dispur Brahmanda, but we did not know so much about it.
Thank you very much. Thank you very much.
So, now I feel very small particle in this whole universe. Our existence is very non-existent almost. Two questions. I think we know so much. This small virus. Can we find out some radiation by which you can destroy the virus? Number one. Number two, not medicine, but some radiation. Number two, I want to establish one telescope in our university. Okay. Not to see the galaxy, but to see the moon and the Mars and the Jupiter or Saturn. Sunandan Bora. Okay. You please see that it can be done at a not very huge cost. Yeah. And then saying, I'm thrilled to see your lecture. Then I have seen that Know Your Universe, that this Discovery channel. They sometimes scare you. There are some big meteorites roaming around, and sometimes it strike the Earth. Is there any possibility in the near future?
Actually, okay, let me deal with it one by one. One thing is that I think putting an optical telescope is a wonderful idea. I know that Professor Talukdar, when he was there at ISST, he also tried to get a small telescope installed over there. I mean, it is not only important for the community of the university, but I think it's also an important component for outreach programs of the university. Because you can get children from the surrounding villages and areas to enthuse them about science, to look through a telescope and watch the night sky. And Panikhaiti being far from Guwahati city, the light conditions would be far more favorable than in Guwahati city to watch the night sky. So I think that would be a wonderful thing to do, to try and put a small size optical telescope so that at least the planets and some of the nearby galaxies that you can observe from the site at Panikhaiti. I think that would be wonderful. Yeah, and I think I'm sure Professor Talukdar would probably take it up, and from my side, I'll definitely be happy to help with whatever context I have, and that would be absolutely wonderful. Now, as far as destroying the virus is concerned, the thing is that I mean, you can't do it in the human body, right? Because radiation that will destroy a virus will also destroy a lot of other cells, and this is so widespread. I mean, radiation therapy has been used for cancer cells which are localized, which may be localized. So it will be very difficult to do it for a virus by radiation. I mean, you may be able to do it in a lab or something with very high energy things, but I don't think it's feasible as a sort of treatment or prognosis kind of approch. As far as the universe is concerned, I mean, our place, we are just a tiny speck in the universe, as you yourself mentioned. We don't have any special place in the universe. Even in our own galaxy, we are about 8.5 thousand kiloparsecs away from the center of our galaxy. Our sun is a very ordinary star, and there are millions of billions of stars like our sun, and a lot of them will have. Most of them will have planetary systems like us. So I think in terms of understanding the origin of life itself, the origin of life in our planet is of fundamental importance, because that will also give us clues as to how life could or may have originated elsewhere. And I think we cannot be so chauvinistic as to say that we are only we'll only look for life forms we are familiar with, because even in our Earth, we know of anaerobic bacteria which don't rely on oxygen. We know of life forms which survive in sort of dense, hot temperatures, sulfuric acid, sulfur fumes, etc. So life may manifest itself in very different forms in other planetary systems, and we have to be open to all possibilities, I think. Yeah.
Thank you.
Thank you. Thank you very much.
Professor Saike, this is one hypothetical questions, not a questions. Some sort of, something came out. The current scenario, the atmosphere, the environment is free from everything around the globe. No pollution, no vehicle, no factories running. So is it a good time to go for an astronomical research of the world of galaxies?
See, today, actually, I forgot to answer one question of Chancellor, which was the meteorites. Okay, so let me just deal with meteorites, and then so it is not an impossible situation that some meteorite will hit the Earth. After all, meteorites have hit the Earth in the past, and the Arizona sort of crater is been caused by a meteorite, and there are very convincing claims that the disappearance of the dinosaurs may have been due to a meteorite which the Chicxulub in the Mexican Gulf may have hit it. So it is a possibility, and that is why one of the major programs which is carried out has been to monitor the motions of what are called the near-Earth asteroids. So any near object, you monitor it very carefully, so that if there is any hope of trying to sort of change its trajectory, if we have the technology someday, we'll be able to do that. But at least we'll be able to predict what may happen. But considering the frequency at which large meteorites have hit the Earth, it is not going to happen very frequently, but it is not something which can be ruled out. But the way we are going right now, both in terms of destruction of our environment and, I think we'll probably kill ourselves before meteorites hit us, unless we have more responsible governance, both in India and elsewhere. Okay. All right. So it's a possibility, but probabilities are low.
Yeah.
Okay.
Not in our lifetime.
Hopefully not in our lifetime. Not in a lifetime. Actually, if you look at the lifetime, I mean, if everything goes smoothly, the future of the Earth will be governed by the future of the sun, the evolution of the sun. Because in about 4.5 billion years, the sun will expand to become what is called a red giant star, and it will extend much beyond the Earth's orbit. So it's going to gobble us up in its in the sun itself. So if we take care of ourselves, and I think 4.5 billion years will be done with. Okay, Dr. Uni, your question. Actually, when we do astronomical observations and we make telescopes, we try to fix sites which are ideal for that. That is why that, for example, I showed you the image about how the atmosphere cuts off radiation. So, for example, if I want to make a millimeter wave telescope, I would put it at a site which is as high as possible and with very low atmosphere. If I want to make a good optical telescope also, I will try and put it high up on a mountaintop where the effects of the atmosphere are minimized. So all good telescopes, you look for a good site to start with, because you're investing money and resources and you want a telescope to do well for a long time. So this temporary thing of lack of lower pollution because of people being indoors or driving less because of the lockdown is not in any way going to affect where you put these telescopes, because they're anyway sort of looked at and put in places of very low human habitation, very low pollution, very low atmospheric effects, and all that. Yeah.
Thank you.
Yeah.
Professor Sekia.
Yeah, Professor Talukdar.
We have only 3 or 4 physics faculty.
Okay.
And I'm not sure whether they have they are attending this talk.
Okay.
When you said that radio wavelengths, what
Yes.
is it's the upper limits, like, and which portion is used for mostly generating information that you have shown? Like,
yeah, actually, the thing is that right now, most of the radio observations which we do comes from a wavelength of millimeters, where, for example, carbon monoxide, if you want to do molecular studies as well, so from about a millimeter to a few tens of meters. And the reason why we are not able to do observations routinely at longer wavelengths is because the ionosphere actually cuts off those radiation from reaching us. Okay, so there may be interesting physics at longer wavelengths than that. And to probe that physics at longer wavelengths, where the ionosphere is not cutting us off, there have been talk about putting a low frequency telescope on the moon, perhaps on the far side of the moon, so that you're even cut off from any man-made interference on the Earth, which is the moon. On the far side of the moon, so that you study what is possible at long wavelengths. So today there are a lot of interesting questions at these long wavelengths as well, which we are not able to probe. We're doing a little bit via space probes which go above the ionosphere, but there is a whole regime to be explored, which is not been done because the ionosphere cuts us off. The ionosphere also varies on geographical location. So, for example, in New Zealand, select locations where the effects are a little less, and you can go slightly lower in frequency, but also dependent on the solar cycle, because the sun is far more active when there are more sunspots on the 11-year cycle. But basically, the ionosphere is what is cutting us off, and there are talks of putting a telescope on the moon, on the far side of the moon, but that will probably happen not in my lifetime.
Yeah. Like another question, this question is not mine. You perhaps know Garima, my student. Like few years ago, she asked the question, but now I got a right occasion today. I think I'll be able to give some answer from you. What she said, that because you have talked about touch upon astrochemistry and astrobiology, what she asked me that all the spacecraft that goes into space, and they will carry a lot of bacteria and viruses and all sorts of things from Earth, because it doesn't go contamination free. She asked me, sir, what will happen to those bacteria? Some of them will be left over in the space. What will happen to those? It is a real question she asked, but I couldn't answer anything. And can there be a way of detecting those? If like there could be two things. One to evolution of life in astrobiological origin. That's a different issue. But those which the spacecraft carry and live there, because many of them will escape. So can there be a way of knowing all those?
Okay, perhaps carrying viruses and bacteria, or how much of it, because they're usually made in ultra clean environments, and
Okay.
then transported. They try to keep it as ultra clean as possible, because ultimately what happens is that even the spacecrafts which are going out, particularly the manned ones, they're going to live there for quite some time. So they try to actually keep it in an absolutely ultra clean environment. Okay. But in terms of trying to understand the formation of life elsewhere, I mean, we have, the whole field of astrobiology has developed quite a lot in recent times in trying to put together what we have understood in biology and try to, construct plausible scenarios in which life may have originated elsewhere or not. And also there have been some interesting findings, like for this handedness of amino acids, that the life forms we know of today have only one-sided amino acids. You'll know that much better than I do. And but for example, when we pick up samples from meteorites, from asteroids, are we going to see different handedness of them? Are we going to see both handedness? So the kind of questions which are related to the ingredients which make up life, I think that is something which we will get a better handle on when we get more samples from outside. And that is something which is extremely interesting to study as well. In fact, some people thought that life may have been brought down by these comets. But I don't think, serious biologists actually buy that. Vikram Singh, who tried to suggest that life may have originated from comets which brought it to the Earth. But I don't think any serious biologists actually buy that. But it's an open question, and I think progress is being made. A lot of progress has been made, but maybe someday one can discuss formation of life and astrobiology on a different day. But there are a lot of interesting things which are happening on that front as well.
Thank you.
There was a question on the chat which said that, does the solar wind also vary with solar cycle? Solar wind does vary. Solar wind in the sense that the solar wind consists of various components, including very fast traveling disturbances as well, and these are far more active when during cycles of solar maximum than solar minimum. In fact, monitoring the space weather, as it is called, which is basically the effect of the solar wind, is something which is very important, because it is important for communications, is important for aircrafts, and there have been instances of where charged particles have come and burned down power stations in the northern hemisphere because of magnetic field structure. You get it more easily to get there. So the solar wind also does vary with the solar cycle, and it is important to monitor them. And a lot of energy and resources are being spent on monitoring the space weather, as it is called here.
Professor Saikya, I have a small query.
Please, yeah.
Am I audible, Professor Das here?
Yeah, sure, you're audible,
Yeah. So, as you have said that there are different areas of astrophysics and astrobiology and astrochemistry.
Yeah.
Then basically the problem that we are going to face, or it's the verge of very severe condition, that's the climate change and the air quality surrounding our planet. So is there any way out to clean our air as well as to have some ameliorating effect in the climate change?
Ameliorating change by what? Sorry, I missed that point.
Maybe because through your studies, whatever astrochemistry, astrobiology you have, methodology.
See, my own sort of my own thought on this is that as far as climate change is concerned, it's happening, and to actually seriously address the problem, you need political will. And today, even at the highest levels, you have not only denial of climate change, but even reckless destroying of the environment. And you have seen this in the last during this last 5 or 10 years as well. You look at a number of projects which have been sanctioned, which has actually decimated our wildlife resources. And this is something. I mean, you had Trump over there for a long time who actively denied climate change, and so there's strong economic and political interests, political lobbies, and I think we have to keep the pressure up in addressing that. But I think unless there is political will, the amount of degree of success you have would be limited. But there are also countries which are making a lot of progress. I mean, Germany has switched in a major way to environmentally friendly power, and that consciousness is actually developing in many other European countries as well. You can see effect of climate change in many ways. I will tell you, for example, the cherry blossom tree, which flowers, and the flowering depends on the temperature. So there were a couple of scientists from Japan, Kyoto, and another university who looked at the flowering of the cherry tree at the peak of time of maximum blossom from the time of when Kyoto was the capital, so hundreds of years ago. And they have collected all kind of archival records, and they've correlated this with when temperature records became available, and there was an observatory over there. And they found a nice correlation between when the temperature changes and when the maximum flowering occurs. Now, in the last decade or so, you can see the time is coming earlier and earlier. Just by looking at the flowering of a cherry blossom tree, you can say that the Earth is warming up. Forget fantastic science. But yet, you have strong commercial and political interests, politicians who want to cater to their coteries, that you're actually destroying the environment, whether it be in India or elsewhere. So that political pressure has to be there, that consciousness has to be there among the people, that awareness has to be there, so that people who are actually destroying the environment get voted out of power. So, I don't think just sitting at the desk and working away will actually solve the problem.
Absolutely, I agree. Like, unless science and politics are in the same platform, a future of the entire humanity I think, is at stake. Absolutely. And like what you said, that's very interesting. This cherry blossom flowering and temperature. See, if you talk of Northeast India, the biodiversity hotspots, all these plants, it's flowering behavior, phenology, they are responding to that climate change, the temperature change, only a matter of record. But we don't have any project or like massive thinking where we can have record of some of the very important indigenous plant. If suppose we had the last 100 years record of how the blooming time, that itself orchid bloom effect, because I had small observation 2-3 years ago that year the temperature in March itself, temperature was like your April temperature, and the Rinko stylis, that orchid, I saw generally orchids bloom that coincides with your Bohag Bihu time, right? So like that small things are happening, but if we long-term record, if we keep, it will become very obvious. Like it's a cherry blossom is one example. If there is good support, research project, there is support to keep this record and analyze, scientific analysis is done, a lot of things can happen actually.
Absolutely, Professor Talukdar. I will send you a copy of that paper if you have not seen it.
Sure, please. Yeah.
Okay.
Thank you.
But I think phenology as an area, I think it would be wonderful if you started off in Assam Downtown University.
That is what I am planning now. Yeah, at least for years we can start this activity.
Yeah. I want to know at least for future generations. There will be something behind there.
Another point just I want to add, if you see the 100-200 years history of diseases, emerging, re-emerging diseases in man and animals, the entire scenario is gradually changing, and only maybe because of climate change, maybe because of other reasons. But that's what we need to concentrate, so that we understand the evolution of even the diseases and all that.
I think so. I think so. I mean, the thing is that zoonotic diseases will probably become more common, I think, and as we are destroying our forests, getting closer to it, and in Assam, we still don't have, we need more